You probably think of electric vehicle charging as this static, maybe slightly annoying process.
Yeah, pulling into a sad, empty parking lot.
Exactly. You find a plug, you park, and you just wait. It feels like fueling up a vehicle has essentially been the same for a century, just, swapping a traditional gas pump for a really heavy electrical cable.
Right, the core user experience hasn't really changed much.
Right. But what if, and think about this, what if instead of you driving around to find the charger could physically navigate a parking lot to find your car?
Which is wild to think about.
Totally wild. Or what if an 18-wheeler could suck down enough electricity to drive hundreds of miles in the time it takes you to eat a sandwich?
Yeah, or, and this is my favorite one, what if your pickup truck actually paid you to keep your neighbor's lights on during a blackout?
I mean, it sounds like science fiction. But looking across the stack of global infrastructure blueprints we have for today's deep dive, from U.S. Energy Department technical manuals to Chinese urban deployment trackers, it's happening right now.
It really is. We are right in the middle of a massive, basically invisible rewiring of the entire energy grid.
And that invisible transition is exactly what our mission is today. We want to decode this radical rewiring happening right under your nose, because we're looking at these ingenious, almost surprisingly creative workarounds that are solving the single biggest threat to the EV transition.
Right, the infrastructure bottleneck.
Exactly.
Yeah.
Like, we have the cars on the road, right? The battery technology is totally proven. But the traditional power grid was absolutely not built to handle millions of massive high-speed power draws.
No, not at all. The issue at its core is it's really about predictability. For over a century, power grids were designed to handle these slow, predictable, steady loads.
Like a neighborhood waking up.
Yeah, exactly. People waking up, turning on the lights, maybe making a pot of coffee. The grid operators can see that slow ramp up coming from miles away.
Makes sense.
But when we talk about modern direct current fast charging, or DCFC, we're talking about a massive, instantaneous, and highly unpredictable amount of electricity.
Right. Because according to the technical help sheets we're looking at, a single modern fast charging station can require 600 kilowatts or more the actual second a vehicle plugs in.
Which is just a staggering amount of power.
It is. To put that into perspective for you, that's the equivalent of an entire block of homes instantly turning on every single appliance they own at the exact same millisecond.
And older local power grids just, they cannot handle that sudden, violent pull of power.
Yeah, I mean, if you string 4 or 5 of these chargers together at, say, a rural gas station, you are talking about industrial-level power requirements on a completely residential-level grid.
And that harsh reality is what forced the Joint Office of Energy and Transportation to heavily promote this really brilliant workaround. It's called battery buffered fast charging.
Battery buffered fast charging.
Right. So instead of pulling power directly from the grid to the car, engineers are placing a giant stationary battery exactly between them.
Okay, let's unpack this because I love the analogy for this. It's exactly like the tank on a standard toilet.
Oh, that's actually a great way to think about it.
Right. You have this tiny, narrow pipe coming from the wall, and it's slowly filling the water tank over a couple of minutes. If you tried to flush a toilet using just the water pressure from that tiny pipe,
It wouldn't work at all.
right, it wouldn't work. The flow rate is just way too weak. But because the tank stores that water up, when you flush, you get a massive, instantaneous rush of water that the small pipe could never deliver on its own.
And that physical mechanism maps perfectly to the electrical reality we're seeing here. The stationary battery slowly and continuously sips power from the local grid 24 hours a day.
Just pulling an amount the grid can easily tolerate.
Exactly. Then, when an EV pulls up, the station basically gulps that stored energy rapidly right into the vehicle. And the impact of this simple buffer is, it's staggering.
What do the numbers look like?
Well, analysis by the National Renewable Energy Laboratory shows this setup reduces the need for heavy grid upgrades by 50 to 80%.
Wow, 50 to 80%.
Yeah. So you completely avoid trenching up miles of rural roads to lay massive new electrical cables just to support a few highway chargers.
And it doesn't just save on construction costs, right? It fundamentally changes the daily operating costs because of how utility companies actually bill commercial locations. It avoids demand charges.
Yes, utility billing for commercial sites is notoriously complex. They don't just charge for the total volume of electricity used over a month. They charge a massive premium for the maximum width of the pipe you required at any given moment.
So if you spike the grid just once for 10 minutes to charge a single car.
You pay a massive demand fee for the entire billing cycle. It's brutal. But by using the battery buffer to slowly sip power, the station avoids those massive demand spikes entirely.
Peak shaving.
Exactly. In the industry, this is known as peak shaving.
Beyond the cost savings, though, the resiliency aspect is fascinating to me. The reports note that a 500 kilowatt-hour stationary battery can keep a rural charging station running for up to 10 hours during a total grid blackout.
Which is huge for emergencies.
Right. If a storm knocks out local power, the station is still actively dispensing juice to stranded drivers.
Right.
But how do engineers actually know how big of a toilet tank to build for these stations? I mean, you wouldn't want a battery so small that it drains after 2 cars.
Right, so they size them based on 2 highly specific criteria. The first is called the first hour metric.
First hour.
Yeah, this basically tests whether the battery can handle a sudden, massive surge of cars arriving all at once. Say, 4 cars pulling up simultaneously to a lightly utilized station.
Okay, so a sudden rush.
Right. The battery has to absorb that immediate shock without tapping the local grid. The second metric is the design day, and this is more about long-term capacity planning.
Right, planning for the worst-case scenario.
Precisely. They model for the absolute heaviest day of demand imaginable, like the 99th percentile busiest holiday travel weekend projected for, say, the year 2030. They have to ensure the station doesn't just run dry when a continuous stream of travelers is relying on it.
If we connect this to the bigger picture, that changes the financial math completely for rural and low-income areas. It allows a small town to install high-speed chargers right now without having to wait a decade for the regional utility company to approve and rebuild the local transmission line.
It really does. But that toilet tank solution does have a fatal flaw.
Oh, what that?
It still requires a physical footprint.
Right.
You still need concrete, you need a dedicated parking space, and you need at least some connection to a grid to slowly fill the battery. So what do you do in an urban environment that was entirely paved 50 years ago with zero room to spare?
And that is the exact wall they hit in Nanning, China. Our sources detail this specific residential neighborhood there called Linlikou Jiaiwan. It's an older, super densely packed housing complex.
Right, the kind with absolutely no extra space.
None at all. And the residents collectively own over 400 electric vehicles, but the neighborhood has absolutely zero grid capacity to add permanent chargers, and no fixed parking spots to install them in, even if they did have the power.
So the urban planning of the past collided head-on with modern technology.
Exactly. And the solution there came from a company called Energy, which introduced something called the energy tank.
Which is just a wild piece of tech.
It really is. Instead of bolting the battery buffer to the ground, they made it mobile. It's a 1.5-meter tall, self-guided robotic battery.
So a resident simply pulls into a random available spot, takes out their phone, and summons the robot via an app.
Yep. The robot, which houses a 100 kilowatt-hour battery, autonomously drives directly over to the parked car and can charge it from 10% to full in about 40 to 60 minutes.
You literally order the electricity to your specific parking spot like you're ordering food delivery.
Exactly like food delivery.
Yeah.
And it's gaining traction beyond just dense neighborhoods, too. The battery giant CATL deployed a similar fleet of robots called Chargo at highway rest stops during the really busy Spring Festival in China.
Right, so instead of drivers waiting in line for a physical plug, the robots just drive down the line of waiting cars, charging them right where they sat.
Which is brilliant.
And we are also seeing this logic applied to completely off-grid situations now.
Yeah.
Down in Australia, a company called Alpine Energy launched the MGEN system. This is the world's first vehicle-to-vehicle DC fast charger.
Wait, vehicle-to-vehicle?
Yeah, it requires absolutely zero grid infrastructure. The charging hardware is mounted directly into the bed of a donor vehicle.
Oh, wow.
Yeah, they used a BYD Shart 6, which carries a nearly 30 kilowatt-hour battery of its own. It literally just drives to wherever the energy is needed, whether that's rural breakdown assistance, emergency response, or, powering a fleet at a temporary outdoor construction site.
Here's where it gets really interesting, though, because from a physics perspective, isn't it wildly inefficient to use a massive battery to literally drive another massive battery across town? I mean, you're burning energy just to move the mass of the energy delivery system. The thermodynamics seem entirely counterproductive.
I mean, from a pure thermodynamic standpoint, yes, you are correct. There is an undeniable energy loss in moving the mass of the delivery vehicle.
Right.
But you have to weigh that operational inefficiency against the capital alternative.
The cost of building.
Exactly. The amount of money, time, and carbon emissions saved by avoiding digging up city streets, ripping out old electrical infrastructure, and pouring concrete, it's monumental.
That makes a lot of sense.
It completely reframes the challenge. You're no longer trying to solve a static real estate problem.
Yeah.
You are solving a dynamic service delivery problem.
It turns charging into a logistics network rather than a construction project.
Exactly.
And speaking of avoiding construction, there's a fascinating software-based solution detailed in the reports out of India that achieves a similar goal, but without deploying a single robot.
Right. The software side is huge.
Two companies, Bolt Earth and ChargeZone, partnered up to solve what they call the car finds a pile problem. They essentially took over 1,500 existing isolated fast charging stations across the country and unified them onto a single interoperable app.
Which proves that the infrastructure bottleneck isn't strictly about hardware. Sometimes the bottleneck is just user access and data visibility.
Yeah, if a driver has to juggle 5 different proprietary apps, preload balances on all of them, and then guess which network has a working plug?
The system is failing. But by unifying those fragmented networks, they effectively eliminated range anxiety for thousands of drivers without laying a single inch of new cable. Unlocking stranded capacity is just as vital as building new capacity.
Absolutely. So, okay, we have a pretty clear picture of how passenger car charging is evolving, but we need to shift our focus to the giants of the road. Heavy-duty trucks.
Ah, yes, the heavyweights.
According to the data, these commercial trucks account for a massive 40% of all transport carbon emissions. If we don't fix the freight sector, we're just tweaking at the margins of global emissions.
And the heavy-duty sector is facing an entirely different set of constraints. Economically, the transition actually makes complete sense today. Like in China, the total cost of ownership, meaning the purchase price plus fuel and maintenance for an electric heavy truck, is already vastly cheaper than a traditional diesel truck.
Really?
Yeah.
Vastly cheaper.
Oh, yeah. Fleet operators are looking at spending about $91,200 annually for an EV truck versus $117,200 for a fuel truck.
Why? So a $26,000 annual advantage per vehicle. You would assume every truck on the road would be electric by tomorrow with those numbers. But there's a catch, right?
Always a catch. And the catch here is gravity.
Gravity.
Yep. For short-haul routes, think port operations moving containers a few miles or mining trucks running closed loops, the transition is already massive. The penetration rate for short-haul electric trucks in China is currently over 60%.
Which is incredible.
It is. But long-haul logistics is where the physics bite back. Global regulations cap the total gross weight of heavy-duty trucks to protect the roads. In many places, that cap is 49 tons.
Okay.
If a logistics company wants a truck to drive further without stopping, they have to add more battery packs. But batteries are incredibly dense and heavy.
Oh, I see.
Yeah, every pound of battery you add to the truck is a pound of paying cargo you can no longer legally carry. And cargo weight is the sole metric that determines a route's profitability.
Ah, the weight loss for cargo problem. So to solve it, you either need lighter batteries, which is obviously a really slow material science problem, or you need to charge so fast that the truck only needs a small battery to begin with.
Exactly.
And our blueprints show the global industry is currently split on 2 completely different heavyweight solutions to this. First, we have battery swapping.
Right, swapping.
CATL is building a massive network in China, aiming for 900 swap stations by 2026. A truck pulls into a bay, an automated machine drops the empty battery out from underneath, shoves a fully charged one in, and the truck rolls out in minutes.
And battery swapping elegantly solves the charging downtime issue, but it also fundamentally changes the financial model. Fleet operators can purchase the physical truck shell but lease the batteries as a service.
Oh, that's clever.
Yeah, this dramatically lowers the initial upfront cost of the vehicle, removing a massive barrier to entry for smaller logistics companies.
But Europe and the US seem to be betting heavily on a competing global standard, megawatt charging systems, or MCS.
And the specs on MCS are staggering.
They really are. We're talking about delivering up to 3.75 megawatts of continuous power. That is roughly 10 times the power of the absolute fastest passenger car chargers operating today.
And the engineering required to push that much power is intense. When you push 12,250 volts of direct current through a cable, the sheer volume of electricity generates extreme heat.
It must.
Yeah, so the cables and connectors for MCS actually have hollow conduits built into them, where a specialized liquid coolant flows constantly, absorbing the heat to ensure the cable doesn't literally melt into the pavement while it's attached to the truck.
So battery swapping is basically the Pony Express. Instead of resting the horse, you just swap it out for a fresh one. But megawatt charging is like keeping the same horse, but somehow feeding it 50,000 calories in 30 minutes without it exploding.
What's fascinating here is how perfectly that 30 to 40-minute megawatt charge aligns with human limitations.
Human limitation.
Yeah. In the European Union, the law strictly mandates that commercial truck drivers must take a 45-minute rest period after every 4.5 hours of driving.
Oh, wow.
Because megawatt charging can fill a truck's battery in under 40 minutes, it fits seamlessly within this legally mandated human downtime.
So the bureaucratic red tape actually created the perfect window for the technology. The technological limitation of the battery charging speed becomes entirely invisible to the logistics schedule.
Precisely. The truck is legally forced to stop anyway, so the charging process doesn't cost the logistics company a single minute of transit time. The technology bends to accommodate the human regulation, completely neutralizing the primary argument against long-haul EV viability.
All right, we need to look at the final and maybe most profound reveal from these sources. Up until now, everything we've discussed involves vehicles acting as massive energy consumers, draining power from the grid.
Right, pulling power out.
But the blueprints show a rapidly accelerating movement to reverse that flow entirely.
Which is where things get really futuristic. We're moving from a world where EVs are viewed as a burden on the grid to a reality where EVs become the salvation of the grid.
The concept is called Vehicle to Everything, or V2X. And a major pilot program just launched in California that puts this into practice, utilizing a partnership between the utility company PG&E and Tesla's Cybertruck.
Right. So through a system called PowerShare, a Cybertruck owner can now use their vehicle's massive internal battery to literally power their entire home during a blackout.
But the pilot program goes much further than just, keeping the fridge running when a tree falls on a power line. Through PG&E's Emergency Load Reduction Program, these truck owners can actively sell their stored vehicle power back to the grid during times of peak public demand.
Just think about a severe summer heat wave. Everyone comes home at 5:00 p.m. and turns on their air conditioning. The grid nears total collapse due to the sudden demand spike.
Right.
Instead of firing up dirty, expensive peaker power plants, PG&E can send a digital signal to enrolled Cybertrucks sitting in residential driveways.
And then what?
Those trucks autonomously begin discharging a portion of their stored energy back into the neighborhood grid, balancing the local supply and demand in real time. And the utility actually pays the truck owners for providing that critical stability.
Wow.
In this pilot, participants are receiving up to $4,500 in incentives just to install the necessary gateway equipment and stay enrolled.
The technical detail in the report that stands out here, though, is that this is the first AC-based vehicle-to-grid application approved in California.
Which is a massive distinction.
To explain why that is such a massive breakthrough, we have to look at the hardware. Historically, if you wanted your vehicle to power your house or the grid, you had to buy a massive, highly specialized piece of hardware for your garage wall.
Right, you needed a complex external inverter to convert the car's direct current, or DC, into the alternating current, or AC, that your home uses.
And it was easily a $10,000 retrofitting project just for the hardware.
And that cost alone absolutely killed mass adoption. But the breakthrough with the Cybertruck, and what will inevitably become the industry standard, is that the heavy-duty inverter is built right inside the truck itself. The vehicle spits out AC power directly.
So instead of buying and permitting a massive industrial wall box, you are essentially just plugging the truck straight into your home's standard electrical breaker panel using conventional residential wiring.
It dramatically lowers the hardware complexity and installation costs, making it accessible to vastly more homeowners.
So what does this all mean? Does this mean when you buy a Cybertruck or any V2X vehicle, you aren't really buying a car in the traditional sense anymore? You're buying a mobile power plant.
This raises an important question. It completely upends the century-old economics of car ownership. I mean, historically, a vehicle is the ultimate depreciating asset, right?
Well, for sure, you drive it off the lot and lose thousands.
Exactly. It sits in your driveway, losing financial value, doing absolutely nothing for 95% of its life. But in a fully realized V2X ecosystem, that vehicle transforms into an active, revenue-generating, flexible energy resource.
It acts as a giant distributed shock absorber for the entire state's electricity grid while you sleep.
It's incredible.
Looking back at the full stack of reports we've dug into today, the scale of this transition is breathtaking. We started with the concept of stationary toilet tank batteries buffering our weak, aging grids to prevent them from melting under the strain of fast chargers.
Right.
Then we saw how urban density forced the creation of autonomous robotic chargers, navigating older neighborhoods to deliver power directly to parked cars.
And then the trucks.
Yeah, we explored the thermal engineering behind megawatt cables force-feeding semi-trucks on the highway, perfectly synced to driver rest mandates. And we ended right in your driveway, with your personal pickup truck autonomously selling power back to the regional utility company during a heat wave.
The static, one-way system of electricity delivery is dead. The energy infrastructure is becoming localized, dynamic, and entirely mobile.
So the next time you see an EV silently drive past you, don't just see a car. You're looking at a localized node in a completely revolutionized energy web. Which leaves us with a rather profound reality to consider. If millions of individual drivers suddenly possess enough stored mobile battery power to sustain entire cities during peak demand events, who actually holds the power in the energy markets of the future? Will it still be the giant traditional utility monopolies calling the shots from a centralized control room, or will the grid be stabilized by a decentralized collective of everyday people parked in their driveways? Something to think about. Keep digging deeper.